So hi all. So as you are aware, uh, this will be a problem solving session. I am Shubhajit Das, one of the TAs for this course, and we will solve some problems based on your whatever you are learning in the entire week. So the problems that I have made are either from the previous year assignments for this particular week one, or and some of the problems are from my side. Okay, so before we start, I'd just like to say a couple of things. That firstly, if you have any questions whenever I'm solving the problems, you can just write them down in the chat, and I'll just uh, do sort of and try to answer them maybe at the end of the session. And also, I would want that this would be I want this to be an interactive session. So it would be great if you would maybe respond, maybe write something in the chat or sometimes. So let me first share my screen. So can someone please respond if you are able to see my screen? Maybe in the chat. Can you see my screen? Okay, thank you so much. Yeah. So we start solving problems now. Okay. So first of all, I know that you have been learning the group axioms and something about the permutation group and maybe conjugacy, order of elements and all that in group theory. So this is preliminary. You are right. You are just at the beginning. So we'll try solving problems, some basic problems. Okay. Yeah. Okay. So so we start with a very simple, basic conceptual question. You know, you are fully aware of what a group is. What are the group axioms? That is a definition of a group. So this is our first question. That can you put a group structure on the empty set? So you are given this. Okay. So you are given this empty set, which, as you know, has no elements in it. So can you put a group structure on this empty set? What I mean by this is, can you define a binary operation to the empty set such that all the three group axioms are satisfied? That is, you have associativity, you have existence of identity, and you have existence of inverses, right? These are the group axioms. So anyone would like to try, maybe? So does anyone want to try this one? Is the question clear? So can you define a group operation on the empty set? An operation that is a binary operation on the empty set such that you have associativity, identity, and existence of inverses, which are the group axioms, right? So maybe someone can write down something in the chat. Yes or no? So maybe no one. Yeah, definitely. I hope you are replying to this question that no, we can't put a group structure, right? Yeah, and you are right, absolutely right, because simply because of the identity axiom, right? Recall what it says, that if you're for a set to be a group, you must have a binary operation on the set. The binary operation should be associative, that is, it should be a semi-group, and moreover you must have existence of an identity element, right? That is existence of an element E, which such that for any element A in your set, AE should be EA, right? I mean A times E is A, which is E times A. But the empty set doesn't have any element in it, right? Let alone the identity element, it doesn't have any element in it, and hence you can never put a group structure on the empty set. That's just impossible. In other words, a group must always be non-empty. It must have at least one element in it. Right. So this was a simple question. We now come to question 2, which is actually from the previous year assignment. So let me just, yeah. So the previous year assignment. So you have learnt about permutations this week. You know that what is Sn, right? Sn is precisely the group of all permutations of the n letters, right? Maybe we can take the n letters to be 1, 2, 3 up to n, and and Sn is just the collection of all permutations of this 1, 2, 3 up to n of this set, right? And you know it forms a group under composition. Each permutation is a mapping. So each permutation is just a mapping of, it's a bijection from this set to itself, and the collection of all such bijections gives you Sn, right? So we can write, so to denote a bijection we can just use this symbol. So the collection of all such bijections together with composition, this is the group Sn, right? Good. So now we define a fixed point of a permutation sigma in Sn to be an element I, which is fixed by the permutation sigma. In other words, it is just an element I in the set 1, 2 up to n, such that sigma fixes I, that is sigma maps I onto itself, right? Right? Yeah. So the question is, so we first define what is a fixed point of a permutation sigma in Sn. Now the question is, how many permutations of Sn have 1 as a fixed point? So, okay, so the term contain is a bit wrong maybe. I mean, so let's write have here. So have 1 as a fixed point. Good. So how many permutations of Sn are there which have 1 as a fixed point? In other words, you are required to find the cardinality of this set, right? So you take permutation sigma in Sn such that sigma of 1 is equal to 1. That is, sigma maps 1 to itself. It may map other elements wherever it wants, but you have just one constraint, that sigma should map 1 to 1. You are required to find the number of such permutations which map 1 to 1, right? Okay. Observe something, that if sigma is a permutation that fixes 1 and that is the only constraint on sigma, then sigma can map the other elements freely, right? In other words, let's call this particular set to be omega, let, okay? So given sigma in omega, then sigma restricted to this set 2, 3 up to n, this is a permutation, right, of 2, 3 up to n, right? And conversely, if you are given a permutation of 2, 3 up to n, yes, good. If you are given a permutation of 2, 3 up to n, then you can just obtain a permutation of Sn, namely which one? You just map 1 to itself and just stitch this given permutation of 2, 3 up to n, right? So what I am trying to suggest here is that this particular set omega, consisting of all permutations which fix 1, this is in 1-to-1 correspondence with the set of all permutations of 2, 3 up to n, right? That is, in other words, It is a set of all it is precisely, it has the same cardinality as the number of permutations of n minus 1 symbols, and you know that that particular number is n minus 1 factorial, right? So yeah, you are right. So n minus 1 factorial will be the answer. Okay, so the third question is again from the previous year assignment. Right, so it's just a terminology and nothing else. So you define, so suppose you take sigma to be a permutation in Sn. So you define a cyclic descent of a permutation sigma of the permutation sigma to be just an integer I from 1 to n, such that sigma of I is strictly greater than sigma of I plus 1 whenever I is less than equal to n minus 1. That is, whenever I is between 1 and n minus 1, sigma of I should be strictly greater than sigma of I plus 1. And if I is equal to n, then sigma of n should be sigma of 1. So a cyclic descent of a permutation sigma is is some integer I such that sigma of I is strictly greater than sigma of I plus 1 if I is between 1 and n minus 1, or if I is equal to n, then sigma of n should be greater than sigma of 1, right? So it's very clear. For example, maybe let's just take a permutation of S5, 1, 3, 4, 2, 5, let's say. So if we are asked what are the cyclic descents of this particular permutation, so observe. So what I mean by this notation is, so you write 1 in the first place, right? So this is the permutation that sends 1 to 1. Then you write 3 in the second place. So this is the permutation that sends 2 to 3. You write 4 in the third place. So this permutation sends 3 to 4, and 4 to 2, and 5 to 5. This is the usual notation that you have been using, right, this week for denoting permutations. Anyways, now observe that clearly, let's call this permutation to be sigma. So sigma is this permutation, and sigma of 3, which is equal to 4, is certainly greater than 2, which is sigma of 4, right? So sigma of 3 is strictly greater than sigma of 4, that is sigma of 3 plus 1. Sigma of 4 is sigma of 3 plus 1. My point is, so you have this one, right? Sigma of sigma of I is strictly greater than sigma of I plus 1 for some I between 1 and n minus 1. I is a cyclic descent by definition. So in other words, you can say that 3 is a cyclic descent, right? Clearly 3 is a cyclic descent of your permutation. So the question is simple. You are asked which of the following sets may occur as a set of cyclic descents of a permutation of S5. You are given 4 options and you are asked to find which of these sets will give a cyclic descent of some permutation of S5, right? So you understand what cyclic descent is. So you are required to find which of these sets can be realized as the set of cyclic descents of some permutation in S5. So let's see. So let's start with the first set, and just a bit of thinking will let you see that indeed this first set is actually the set of cyclic descents of some permutation. Which permutation? So observe one. So if we are considering the first set, that is the set 1 to 5, and if this were the cyclic descent of some permutation of S5, then clearly if 1 is a cyclic descent, then you know that permutation sigma, whose set of cyclic descents is 1 to 5, for that sigma of 1 should be greater than sigma of 2, right? Since 1 is a cyclic descent, so sigma of 1 should be greater than sigma of 2. Then you must have sigma of 2 strictly greater than sigma of 3, since 2 is a cyclic descent, and you must have sigma of 5 strictly greater than, just see the definition, whenever you have I equal to n, in this case n is 5, sigma of n should be strictly greater than sigma of 1 for n to be a cyclic descent, right? So here 5 is a cyclic descent, and hence sigma of 5 should be strictly greater than sigma of 1, and no other such inequalities should hold, because 1 to 5 is precisely the given set. You want this particular set to be the set of cyclic descents. So indeed, maybe you can take this particular permutation. So you want sigma of 1 strictly greater than sigma of 2. So let's take sigma of 1 to be 3. That is, I am mapping 1 to 3. then let's take also sigma of 2 should be greater than sigma of 3. So let's take sigma of 2 to be 2. Let's take 2. So sigma of 2 has to be strictly greater than sigma of 3, means that sigma of 3 has to be 1, right? And then observe that 3 has not been mentioned in the set. In other words, this is sigma of 3 and it should not be greater than sigma of 4, because if it were so, then 3 would also get included in the set, right? So this is not the case, and therefore we can just let's take this to be 4. Yeah, so we define sigma of 4 to be 4. So clearly sigma of 3 is not greater than sigma of 4. That's understandable. And finally 5 has to be a cyclic descent, which means that this relation should be satisfied. That is, so this is sigma of 1, sigma of 2. So sigma of 5 should be greater than sigma of 1, right? So the obvious one, we just take this to be 5. So sigma of 5 is taken to be 5. And indeed you see that clearly this permutation has a cyclic descent at 1, 2, and certainly not at 3, not at 4, because sigma of 4 is not greater than sigma of 5, which is 5. And finally this 5 is also a cyclic descent, right, because sigma of 5 is strictly greater than sigma of 1. Sorry. Also, I would request people who are joining late, maybe from next time you can join right at 3, because I have to keep on admitting participants. Thank you so much. So yeah, so we just saw that, so certainly 1 to 5 is a cyclic descent, and the set and the permutation whose set of cyclic descents is 1 to 5 is, let's say, 3, 2, 1, 4, 5. This is one permutation whose set of cyclic descents is 1 to 5, right? So yeah, let's look at the second one. The second one is again simple to see. So whether 1, 2, 3, 4 is a cyclic set of cyclic descents of some permutation, right? So maybe you can take, so what you need for this is, suppose sigma has as its set of cyclic descents 1, 2, 3, 4. So sigma of 1 should be greater than sigma of 2, which should be greater than sigma of 3, which should be greater than sigma of 4, and 5 cannot be a cyclic descent of this permutation. So what does that mean, or what does that tell you? So it basically says that sigma of 5 should not be greater than sigma of 1, right? In other words, sigma of 5 should be strictly smaller than sigma of 1, right? So you take sigma of 1 to be, let's say 5, you take this one to be 4, take this one to be 3, you take this one to be, yeah, we should also have sigma of 4 greater than sigma of 5, right, because 4 is also a cyclic descent, and you take this one to be 1. So observe that 1 is a cyclic descent because sigma of 1 is strictly greater than sigma of 2. 2 is a cyclic descent because sigma of 2 is strictly greater than sigma of 3. Similarly for 3, similarly for 4. But not for 5, because sigma of 5 is not greater than sigma of 1, which is 5, right? Yeah. So indeed the set of cyclic descents of this permutation is certainly 1, 2, 3, 4. So the permutation that realizes this is 5, 4, 3, 2, 1, right? Yeah. So this is just simple, it's a completely simple question. Now let's come to the next one, whether 1, 2, 3, 4, 5 can be realized as a set of cyclic descents of some permutation. So assume that indeed there is some permutation sigma whose set of cyclic descents is 1, 2, 3, 4, 5. We show that this cannot be the case. Why? Because if sigma has as its set of cyclic descents 1, 2, 3, 4, 5, then clearly sigma of 1 is strictly greater than sigma of 2. Sigma of 2 is strictly greater than sigma of 3. Sigma of 3 is strictly greater than sigma of 4, because 3 is a cyclic descent. Again, sigma of 4 should be strictly greater than sigma of 5 because 5 is a cyclic descent. 4 is a cyclic descent. And finally, since 5 is also a cyclic descent, then sigma of 5 should also be strictly greater than sigma of 1, right? And that's a clear contradiction, because you have sigma of 1 by transitivity of this ordering, sigma of 1 is strictly greater than sigma of 5 you have, and at the same time you have sigma of 5 is strictly greater than sigma of 1, which is a clear contradiction, right? So certainly 1, 2, 3, 4, 5 cannot occur as a set of cyclic descents, right? So 1, 2, 3. So option C is, I mean, it's not an answer. And what about option D? Can the empty set be seen as a set of cyclic descents of some permutation? So we claim that this is also not the case. Okay, so yeah. So assume that there is some permutation sigma, or let's say tau now. Tau is some permutation of S5 which has as its set of cyclic descents the empty set, right? That means that there is no cyclic descent of tau, right? So what does that mean? So that means in particular that tau 1, I mean, since 1 is not in the empty set, 1 cannot be a cyclic descent, and hence tau of 1 should be strictly smaller than tau of 2, right? Again, 2 is not a cyclic descent, so tau of 2 should be strictly smaller than tau of 3. Again the same for 3. Then tau, again the same for 4, so tau of 5. And finally, again 5 is not a cyclic descent, so you must have tau of 5 strictly smaller than tau of 1, right? So you see whatever is happening now is the exact dual of the previous argument. Now you have tau of 1 is strictly smaller than tau of 5, and again you have this constraint that tau of 5 should be strictly smaller than tau of 1, and that's a clear contradiction. So again the empty set cannot occur as a set of cyclic descents of any permutation in S5. So your answers are option A and option B, right? Yeah. So do you have any questions or any doubts so far? In case you have, you can just write them down in the chat. Okay. Right. So let's come to the next question. So before I start answering this one, maybe someone can let me know if you have heard of cyclic groups previously. Have you? I mean, you should have, right, in your bachelor's? Can someone? Sorry? Okay.
Yes, sir.
Yeah, good. Okay, so you have heard of cyclic groups and you have heard of what is a cyclic subgroup of a group, right?
Yes, sir.
Okay, good. So maybe then we can just start this question directly. So just for the people maybe who maybe someone hasn't heard about it, so we just quickly repeat the definition of a cyclic group. So a group G is called a cyclic group if you can find an element A in the group such that every element of the group can be written as a power of A. So what do I mean by this expression A power n? By this I simply mean that you have some binary operation star on the group, right? And A power n is just A being composed with itself n times. So in particular, if n is 0, then A is being composed with itself 0 times, and by convention we take that to be the identity element. A power 2 means A is being composed with itself twice, A star A. And A power minus 3, let's say, is just the inverse of A being composed with itself 3 times. Good. So a group G is called a cyclic group if you can find an element A in the group such that every element of the group is some power of A. Right? Now notice that I am not saying that G, the group that we are talking about, if it is cyclic then it's infinite. In other words, I am not saying, this is just a small remark, I am not saying that this set is infinite, right? You know these things, right? Because it is perfectly possible for A to have a finite order, right? Let's say A can have order n. In that case, this set will have exactly n elements, right? So this notation doesn't mean that this set A power n, where n varies over integers, is an infinite set always. It may be a finite set, but regardless, you should be able to come up with an element A in the group such that every element of the group is some power, some integral power of A, right? And that's the definition of a cyclic group. Similarly, as you said, you know what a cyclic subgroup is, right? That is, you take an element in the group, you consider the subgroup generated by that element, and that subgroup is defined to be the cyclic subgroup. In other words, it is the smallest subgroup of the group containing that particular element. And since you know what subgroups are, they should in particular be closed under the binary operation and inverses. So the cyclic subgroup generated by A will certainly contain all integral powers of A, right? And you can check that the collection of all integral powers of A is itself a subgroup. So precisely the cyclic subgroup generated by A, that is the smallest subgroup of G containing A, is precisely the collection of all integral powers of A. Right? Examples of cyclic groups are, you already know, the group of integers is an example of a cyclic group. Then again Zn, that is the integers modulo n under addition, is also an example of a cyclic group, right? So yeah, so maybe you also have heard of this, that the only cyclic groups up to isomorphism are precisely Z with addition, which is an infinite cyclic group, and Zn with addition, which is the finite cyclic group of order n, right? If you haven't, maybe you can see that in this course. Anyways, let's come to our next question, question 4. So the question is, can you put a cyclic group structure on R? You know the real numbers, right? The set, the collection of real numbers, which is R. Can you put a cyclic group structure on R? In other words, can you define a binary operation on R which makes it into a cyclic group? So maybe someone wants to try. You can just reply in the chat. Can you put a cyclic group structure on R? No, right, okay, so very good, very good. So why do you think it is the case? Why do you think this is the case? Why can't you put a cyclic group structure on R? Yeah, I mean, that's another way of saying that it's not a, you cannot put a cyclic group structure, but what I'm trying to say is why, what is the underlying reason behind this? Why will there be no generator? If you define a binary operation on R, maybe any binary operation, why does it never have a generator for the group? That is what I'm asking. Someone wants to answer? Why is it the case that it will never have a generator? So what I'm saying is, suppose you take R. So suppose you take R with some operation, we don't know what this is. This is just some binary operation on R. So it is a mapping of R cross R into R. Yes, precisely. Very good. Shamraghi Ghosh. Good. So yeah, precisely that's the reason, that suppose you put a binary operation on R, okay. The point is, it can never give you a cyclic group structure on R, because in order to have a cyclic group structure, a necessary condition is that this underlying set should be countable, right? You just look at this one. What you want is G to be every element of G should be some integral power of n, right? So G has to be a power n, where n varies over integers. Now this set may be finite and it can at most be countable, right? That is countably infinite, right? But it can never be uncountable. But R on the other hand is an uncountable set, as you all know from the infamous Cantor's diagonalization argument, right? R is uncountable. So yeah, and that's precisely your reason, right? Since R is uncountable, you can never write down, if it is not possible to put a binary operation on R such that every element of R is some integral power of that, such that there is an element in R such that every element of R is an integral power of some element. In other words, if you could put a cyclic group structure on R, then R would become countable, which is obviously stupid to ask. So the answer to this one will be no. Very good. So let's come to question 5 now. So this is again in the same flavor of the previous question. So question 5 is asking you, whether you can put a cyclic group structure on this set 1 over n, where n varies in natural numbers. You understand the set, right? It is 1 over n, where n varies over natural numbers. Can you put a cyclic group structure on this set? So someone maybe wants to answer. So observe, this set doesn't have the problem as the previous one. This set is certainly not uncountable, this is countable. But the question is, can you put a cyclic group structure on this set? So maybe someone wants to answer. Okay. So observe that this particular set 1 over n, where n varies over natural numbers, this is a countable set, as I said, right? Can you give me an example of a cyclic group which is countably infinite? Anyone? An example of a cyclic group which is countably infinite. You know, right? We just saw it a few minutes back. Someone wants to answer? Yeah, you mean Z with addition, right? And Z star, what does star mean? I don't know. But yeah, I understand what you are saying. Z with addition is an example of a cyclic group, right? Which is incountably infinite and it's cyclic, right? Yeah. Now look at this set. This set is again countably infinite, right? So what does that tell you? On the set level, as far as set theory is concerned, what does this tell you? So Z is countable, as you already know. And you have this set 1 over n, where n varies over natural numbers. This set is also countable. Clearly it's countable. So what does that tell you? At least forget the group structures and everything. At the level of sets, for set theory, what do you know? You precisely have a bijection, right? From this set to this set. Let's call this bijection to be F. You do have a bijection from Z to this set because both are countably infinite sets. Now, as you said already, that Z with addition is a cyclic group, right? So what we can do is we can use this bijection F to carry the additive structure of Z to that on this to our set, which is 1 over n, where n varies over natural numbers. In other words, we can define, this is a very good trick in mathematics, you do it all the time. Whenever you have something that is equipotent with something else, and this original something has some structure, you can carry this structure forward to the other one. You can do this for metric spaces, for groups, for rings, for fields, for any kind of structure, for any kind of mathematical object that you will be encountering in your entire course, right? Okay, so what I am saying is, so define a binary, we need a group structure on our set. So define a binary operation star, let's call this set A, okay, for the sake of simplicity, let's call this A. So star A cross A to A. How do you define it? So observe that since F is a bijection from Z to our set A, every element of the set A can be written as F of n, right, for some unique integer n, because we have a bijection F, that is an injection and a surjection. So every element can be uniquely written, every element of A can be uniquely written as F of n for some unique integer n. So we define F of m star F of n, we define this to be equal to F of m plus n for all m comma n in Z. So clearly this is a mapping of A cross A into A, it's a well defined mapping of A cross A into A because F is a bijection, there is no doubt with that. Now you can check that. So this is what I leave for you. So check that A comma star is a group. This is very easy. What does a bijection essentially do? It just relabels your elements, right? It's just sort of a dictionary, right? So you have something in one language, which as in our case is the domain, and it is getting translated into something in a different language, right? That is what a bijection is. So you can check that A with star is a group, and not only so, it will be a cyclic group. What can we say about a generator of A? You can check that f of 1, So you know 1 is a generator of Z under addition. You can check that f of 1 is a generator of A, comma star. Similarly, -1 is also a generator of the integers under addition, right? You can check that f of -1 will also be a generator. So whatever is happening in Z under addition, the same will happen for the group A comma star, precisely because star has been obtained by pushing the structure, the group structure on Z under F. And notice that we haven't taken F to be any particular bijection. There are a number of bijections between these two sets. You can take any bijection, and each bijection will put a group structure on A. Okay. So that's it. So you have any questions so far? Is it understandable? Maybe someone can reply if you are able to understand what I am saying. So the answer to this will be yes. Yeah. So anyone has any questions, and are people able to understand? Hello. Maybe someone can reply. Someone wants to reply?
Actually, my internet connection got disrupted.
Yeah.
So for sometimes here you just take the mapping from Z plus to 1 by n.
Yes, very good. We take this, it's not any mapping, we take a bijection. There is a bijection, you take any bijection, and using that bijection, what you are doing is you are putting a group structure on the set A, and the precise recipe has been written. So you define a binary operation in this way, you check that A is a group under this binary operation, and also check that f of 1 is a generator of A star. Yeah, thank you Orko Provo for replying. Yeah, okay, fine. So maybe then we can move to the next problem. Actually, we are only allowed to have a meeting for 1 hour because Google Meet only allows meetings for 1 hour. So we need to make the best of it. Okay. So this is the next question. This is again a very concrete group that you have already encountered previously. It's the group of rationals under addition. You know that it's a very familiar group. So the question is whether this group is cyclic. That is, does it have a generator? Does there exist an element A which generates this group? So maybe, okay, very good. Good, very good. So I guess you guys have, yeah, okay. So Q under addition is certainly not cyclic. Yes, very good. And let's just, this is therefore just a revision for you. So let's just quickly run through the argument once again. So assume, on the contrary, that Q with addition has a generator, it is cyclic and has a generator, let's say A over B, okay. And as rationals are usually denoted, we write A over B as you just pull out the GCDs, I mean the common factors, you write them as a ratio of relatively prime integers where B is strictly greater than 0 and A is any integer, okay. So we claim that the subgroup generated by A over B is a proper subset of Q, okay. So this is our claim, and this is very easy to see. So since B is strictly greater than 0, it may be 1, it may be something different, but it is certainly strictly greater than 0, it is an integer. So you know that there exists, by the fundamental theorem of arithmetic, not the fundamental theorem says that you can write it as a product of primes, rather by the infinitude of primes, since the number of primes is infinite, prime integers. So there exists a prime P such that P doesn't divide B. In other words, in the prime factorization of B, P is not present, okay. And this is always there because you have an infinitude of primes. So you can check that 1 over P is certainly not in the subgroup generated by A over B. The subgroup generated by A over B will be the set of all integral multiples. I am saying multiples because the group operation here is addition, it's an additive group. So the subgroup generated by A over B will contain all integral multiples of A over B, and clearly 1 over P can never occur in that subgroup. So 1 over P, even though it's a rational, is not in this subgroup, which is a clear contradiction. I mean, which precisely says that, yeah, the subgroup generated by A over B is certainly a proper subgroup of Q. So certainly Q with addition is not cyclic, right? I guess, yeah. So this gives a contradiction because we assumed initially that Q with addition is cyclic, and we get a contradiction out of it, right? So now we come to a super easy question you have previously done it maybe in your bachelor's, that suppose that G is a group such that for all elements A in G, A square is identity. So you need to prove that G is abelian. This is easy, right? I'll just quickly run through the argument. So you know this, right? J for any group H, I am not writing the binary operation. Why is this writing not coming up? You can see my writing, right, anymore? Oh yeah. Yeah, so for any group H, you know this, that x, y inverse is y inverse x inverse, right, for all elements x, y in H. This is something very standard, that is, you know that x, if x and y are elements in your group, then there is some element which is x star y, that is some element is assigned the expression x star y, I mean some element is assigned to the expression x star y, I mean, yeah, so there is some element x star y in your group, and hence it must also have an inverse, and its inverse is precisely y inverse times x inverse, right? Yeah. Oops, what happened? Just a moment, let's see. I don't know what happened to my screen. Just a moment, it's a technical glitch at this point. You can see my screen, right? But it's not, this thing is not appearing anymore. Ah, here it is. Just a minute, it will come up. Yeah, again you can see my screen, right? So sorry for this 30-second interruption. There's some tech. Sorry, someone said something?
Yes, now we can see.
Yeah. Sorry for this 30-second interruption. Yeah, thank you so much. Sorry for this interruption. Yeah, okay. So you know this, that for any group H, xy inverse is y inverse times x inverse for all xy in H, right? That's a very simple thing that we have studied previously. So we are going to use this one for this particular problem. So take A and B. So we come to this question that G is a group where every element has order, I mean every element satisfies A square is E. So you need to just show that G is abelian. In other words, you just need to show that AB is equal to B times A, right? So take AB in your group G. So you know that AB square, okay. So you just need to show that AB is equal to BA, right? Now AB is equal to AB inverse. Why is this so? Because since every element square is identity, that means that every element is precisely equal to its inverse. Every element is self-invertible. So AB is equal to AB inverse, which is equal to B inverse A inverse, and again since every element is self invertible, so this is just BA, right? And then you are done. It's as simple as that. So for every element A and B in G, you have AB is equal to BA, which just shows that the group G is abelian, right? I hope the argument is very clear. But before we jump to the next question, here is something that I would definitely like to ask you. Can you give me an example of a group G where every element satisfies this property that A square is identity? Can someone give me an example of a group G where every element satisfies this property that A square is identity? Someone maybe? Okay, very good. Kleins 4 group. Very good, very good, very good. Now, can you give me an example of a infinite group in which every element satisfies this property that A square is identity? So, based on what you have done, we know any group which satisfies this particular constraint that for every element A square is identity, that group must be abelian. What I am asking for is an example of an infinite group that satisfies this property. Have you guys heard of direct sum previously, or maybe direct product? Yes, very good, very good. That is, you are taking the infinite direct product of Z2s, right? Copies of Z2. So what? So an example of an infinite group in which every element has order at most 2, that is every element satisfies that A square is identity, is precisely the infinite product. So let's say countably infinite fold product. So I in n Z2, that is, you are taking product of n fold product, natural number fold product of copies of Z2, right? Yeah. So yeah, this one's again very easy. Power set of natural numbers with binary operation intersection of sets. Okay, maybe yeah. That might give you something, right? Yeah, yeah. So the identity element is the entire set, and yeah, I understand your point. And why does every element have inverse, by the way? There you have a problem, right? It's not a group, right, with binary operation intersection of sets. That's not a group, because you see the identity element has to be, if the binary operation is intersection of sets, then the identity element certainly has to be the entire set of natural numbers, right? And if that is the case, then you are not allowed, you are not guaranteed inverses for every element. For example, you can just take the singleton one. So what set when intersected with singleton one gives you the entire set of natural numbers? That's clearly impossible. There is no such set, right? So this is not a group. I'm sorry, but this is not a group. But yeah, you can definitely improve your example, and instead of taking this, you can just take power set of n with symmetric difference operation. So again, it has the screen has frozen. I don't know why, but yeah, let's just give this a moment. Maybe it will appear. Yeah, but power set of natural numbers with the operation of symmetric difference is an example. It's an example. Yeah. Okay. Maybe you are trying to say this, and somehow in a hurry you said something different. Okay. So let's come to our next question, and again we introduce a new definition, but before that I would just like to ask you, so you have the center, you have the notion of the center of a group G, right? You have previously studied it, I suppose. Very good. And maybe this I just leave this to all of you. Oops, I don't know what is the problem going on. Maybe just a moment. So I have to use a different device from next time. Just give me, yeah. Oh. Maybe next time we can do on the Jamboard. I don't know why this is not appearing anymore. Yeah, now it should. Yeah. So I just leave this question for you all. So you have to prove that the center of a group G is a commutative subgroup of G. That's a very standard problem, and I am very sure that you have done this previously. So G might not be commutative, but this particular subgroup, that is the center of the group, is commutative. It's always commutative, right? So we don't have much time left, and let's see. We can discuss two more questions or one more question. Okay, so so you take a fixed natural number n, and suppose that G is a group which has this property that there is exactly one element x of order n. So you are required to answer this whether x is in ZG, surely you can say that x is in ZG, or it might be the case that x might not belong to ZG. That is option B, which is that x may or may not belong to ZG. So which of the two are correct? X definitely belongs to ZG, or x may or may not belong to ZG. I mean, technically, if A is correct, then B is also a correct option. I mean, may or may not. Yeah, so there's a logical glitch in this, but yeah. Okay, so let me just change the option for that. But yeah, anyway, you think about this problem. So maybe I just put x does not belong to this center. Yeah. So anyone wants to try this one? So whether x belongs to the center, or is it the case that x never belongs to the center? Fine. Maybe we have a few minutes left. I'll try again. I'm facing the same problem, but yeah, you can try to reply maybe in the chat. So you are given a group G, and you are said that there is some positive integer n such that the group has exactly one element of order n. Okay. So does that element need to belong to the center? Is it true that that element always belongs to the center? Is it the case that that group always belongs to the center? Yes, it does, right? And why is that so? Simply because of something that you have learned this particular week, right? Which is the notion of conjugacy. So the question is, does x belong to the center or not? and the question is all about conjugacy. Okay, so you just show, so what you need to show that x is in the center, so we want to show that xy is equal to yx, right, for all elements y in your group. You just need to show that x commutes with every element in your group, or equivalently, because of the presence of inverses, you know that this is equivalent to showing that y inverse xy is x for all y in G, right? Now what significant property does x have? Yes. So what significant property does x have? It precisely has this property that every element should have, x is the only element in your group which has order n, right? So just show this order of y inverse xy is equal to the order of x for all elements y in G. And this is where you are going to use this particular structure, this weird structure of conjugacy, that you have some element, you have the inverse of some element multiplied on the left, and you have the inverse of some element of that same, and you have that same element multiplied on the right, right? Yeah. Yeah, Shamrakji, I guess you were trying to write G inverse xj is x and not G, right? Yeah, okay. So order of, you just show that order of y inverse xy is order of x for all elements y in G, right? And then you are simply done. Because if that is the case, then y inverse xy also has the same order as x, and hence they have to be equal, right? Yeah. So I guess we don't have much time left, but let's just try to answer the 10th problem, the 10th question. And I guess the meeting is going to stop automatically in just 3 or 2 minutes. So even if we can't solve this problem, let me just leave to you something to think for this entire week. Okay. So question 10 is, an uncountable group can have only countably many subgroups. So what this means is, does there exist an uncountable group which has precisely countably many subgroups? The number of subgroups of that group is countable. So there exists an uncountable group which has exactly countably many subgroups. So is this true or is this false? Okay, this is true. True, okay. So why do you say so? This is true. It's a good attempt. Why do you say that there is a group which has countably many subgroups? So I'll just leave with a small hint because the meeting will end. So the hint is, try to consider all cyclic subgroups. Try to consider all cyclic subgroups of the group. Yes, this will not be true. Yes, correct.
Because G is the union of all the countable subgroups.
Yes, precisely. Very good. G is the union of all the cyclic subgroups, right? And you know every cyclic subgroup is countable. So if there are countably many subgroups, then in particular this means that there are countably many cyclic subgroups, right? But and you know countable union of countable sets is countable, but your original group is uncountable. So that clearly contradicts the fact that G is the union of all its cyclic subgroups. Yeah, and as simple as that. Okay. So there were two other questions that I wanted to maybe discuss today. This is question 11 and question 12. Question 12 is very simple, but yeah, question 11 is something a bit substantial. But since we don't have time, maybe we can do this next week, or you can just have a look at the uploaded slides. Okay, and that's it from my side. If you have any questions, maybe we won't be able to answer it today, but you can always write them down in the discussion forum. Okay, so that's it for today, and yeah, I'll see you next week. Okay, so bye everyone. Yeah, thank you for joining, and I would request everyone if they could join in maybe right in the beginning. Okay, that would be great. Okay, so bye. So I'll stop sharing. Okay. So bye everyone.